Okay, we are live and yeah, we're live. This week we're going through some Python algorithms. I know, if you've not been here before, Christina. Oh, I am Christina. I am a data scientist, been doing it over a decade, and now I'm going back to kind of review. I do it every few years. Python algorithms because I don't use them every day. I mean, the part of data science I worked in is more business oriented, so I'm solving business problems and or making business use cases and running experimentations or setting up architectures or not necessarily needing Python algorithms. So I'm reviewing algorithms starting with stacks so that I can complete LeetCode problems. And this week, yesterday, I went over reviewing stacks from my textbook on Runstone Academy. And today I am trying to complete LeetCode problems, realizing that I do not understand what these problems are saying. My brain just doesn't think like that. So this is the one I've been on because I've already started working on it today. But I'm looking on a binary tree in order traversal, right? And so I know what a binary tree is. So this is 2. You have 1 and 3 here, which are like the branches, right? And they want, given the root of the binary tree, return the in order traversal of the node's values. So the in order would be 1, 3, and then the center would be 2 at the end. So you have to do this order. If it's empty, return empty. If it's 1, return 1, right? And they give you these parameters of the range of the nodes and the values. And there's a few different ways you could do it. So since I didn't understand what they were doing, I didn't understand if I needed, I didn't know how to make the tree. So here, they actually have a free editorial for this particular problem. And you can do recursive, which I'm not going to do. A lot of people don't do recursive, but I'm going to look at iteration. And I was reviewing their solution, which does work for how it works. And I'm realizing they have a built-in tree node that they created, and they're kind of using that in this solution here to make it possible, because if not, you'd have to build your own left, right iteration. And so I was looking up like a Python binary tree, and I wonder if I can just make more stacks, because I don't want to be dependent on their built-in tree node necessarily, because I don't think that's going to help me if I don't know how to actually build that. And so they create their own class of nodes, it looks like is how it's constructed. And you can go left on one side and right on the other side, and you'd have to build that out. Since they built that out for us, I was trying to get it to run separately because I like to put print statements in between all of them just to see what's happening. But I don't think I'm going to be able to do that because I can't do print cur. I don't think it'll print out here. Okay, it will print out. Okay, so they process. Let me. This is kind of the formatting. I'm guessing that's the input. So I thought the input would look more like root. Okay, so I guess if that's the full input, then no, it's not a list. And so I guess this is converting it out. this turning root into this format that they have built in, which they have. Oh, I didn't even see this up top. I'm blind, and I've been looking at this for I did an hour before I took a break. I am so blind. Okay, so this is the tree node definition. So you can use these to help you do the traverse because they built it in for you. It's going to pop out the list on return. Okay, so this is it. And we have the value 1, 2, and 3. So we have the value 1 to the left is none, and to the right is 2, and to the left of the right is 3. Okay, so while this is still or stack, so let's print stack. So if I print cur, I print stack a few times and then it changes on the last one. So I print, and then let's make this more readable. We're going to print cur 2 cur. Print cur 2 cur. I'm going to do the same thing here. I'm going to change this to, actually make that cur 3. Cur 3. So I can get the iterations printed out and understand what it's doing, because I'm not sure I do. Stack 1. And then we're going to call this stack 2. We're going to put another stack up there. So what we're going to do here, and this stack should be empty if you're starting it from the beginning. Okay, so when we go in here, cur 3, stack.append cur, we'll print stack, so we have stack 3, and then we're going to print cur. Cur 4, and then we're going to print cur 4, cur 5, and here we're going to print cur 6, and we're going to print res 1. Res. Okay. Now let's look at this. So stack on the first run is 0. This should be cur 1. Let's run that again. I don't want to be confused. Okay, stack on the first run is 0. Cur 1 is the tree node that it is that we input. Now, when we get in here, stack is still 0 because we haven't done anything. And now let's look at how cur 2 does. So this does what? On the inside of here, cur 2 is still the same thing. Nothing's updated with this statement at all. It's still the same. Everything's there and everything's empty. So now with cur 3 on this round, nothing has happened. But we don't have anything happening with stack. It's not telling me anything for stack 3. No, here we go. The first one, stack 3. After you do cur 3 here. So yeah, we have stack 3, it appends. So what changes? Right 2, tree node 3, left none, right none, right none is now stacked. So now curve 4 is still none. After you curve left here, I might need to make this a fancier thing because I'm not seeing what this code is updating. Oh, so here we popped off one when we did here. That was the last time it was 1. They added 1 here and this node changed. Just 2 and left 3. It stayed like that until you popped it off, the 2 off, and you left with 3. Then it fed back. Right, so when we get back, now we're looking at stack 3. That stack is now bigger. It has that on it. Cursor 5 still only has 3. But if you get the remaining, it's 1 and it's 3. Because it popped 3 first because it went left, then it went right. So if I pinned the first one, which is 1, I went to the next one, it was null. So wild curve. So it pops out of that and it pops the stack. Let's start back here. So when we append, this pops 1 off and appends the value of the cursor. Then it goes right. So it chooses to the right, which is this whole node with 2 and 3. Because it's still in that same loop, we are now going to start with the left. That's how we got 3. Okay. I am following. Okay. Now, is anyone the tutorial's fine. Okay. Whew. That was let me submit this. So this one provided by them is fairly slow, and I always check both. So I want to come up here and see what this person did differently. They if not root, return empty. So that covers the empty. And then this one uses recursion. Those were faster. I don't really like recursion. Why? Because I find it harder to remember how to do. Got it. So if I want it any faster, these are going to be recursive options. Okay. So next, this binary tree pre-order traversal. I'm guessing it's like the runstone. I have the lessons up. infix, prefix, postfix that I didn't quite understand. I feel like it's not about the math, it's about the items that you're sorting, and I'm not separating it in my mind. I'm thinking it's like this is math. Math is solved this way. Math is not solved that way. Now for computer science, it's just a representation of the problem you want to be able to do. Okay. Binary tree pre-order. So let's see if I'm going to start with replicating that code from the previous one without looking at it, and then we will change the order that we're iterating through. So we're going to create a result array, a list. We're going to create a stack, and we're going to set cur equal to root, which actually I don't know why we're doing that. Don't think it matters. So while root while root is something, the logic is go to the left, go to the right. So you're going to have root dot left, you're going to have stack dot append root, then you're going to have stack dot hop root, then you're going to have stack dot hop, then you're going to have press dot append root, I'm missing like 5 lines of code here. Let's go back here. Cur val. I have to append the value. I was wondering that. And it's at the top of the page too. Okay. Let's get rid of my print statements. That's why. Well, cur or stack. So while I guess there's something there, I need to figure that out. So why is it or stack? Actually, let's do it without that and see what happens. Best way to learn and remember. So I think that is correct. I need to return the result. And I'm definitely going in the wrong direction for first and second. And I also didn't go right. Need to cur equal cur dot right. Cur equal stack dot pop. Fascinating. Okay. runtime limit. So, so root equal stack pop, and then this is root equal root dot right. And root equal root dot left. Okay, I don't need this extra. I don't think that. I think the or stack might be stopping it from going. And then also, we did left then right. So I wonder if I do left here and yeah, let's see. So this runs, it gets 0 and it gets 1, but it's not actually getting 2 or 3. So we're going to figure that out. So the OR stack keeps it from looping through to infinity and beyond. So the traversal, it can't only go left because 2 is to the right. And I want to go left first. So given the root of the binary tree, return the pre-traversal of its node's value. And that's kind of the order that is currently in, which I don't know how to do. Not at all. I think looking up the binary tree traversal will just give me the answer. And I don't want to just look up the answer. I have the basic format that I need to know. So what is the logic of this, right? If I look at the original post and I go to the editorial that they did give me, start at 1, 2, 4, pop, right, left, pop. One, 2, 4, pop, go back up. So I think it has something to do with this part. But what with that part, I still need to append the 1. Do I do like left, left, right? Or maybe it's just cur. Like if I print cur, let's do that. Oh, let's print this one. This is all I'm working on. Okay. This has value 1. There's nothing to its right, so we need to go to the left. I mean, it's nothing to the left of it, so we need to go to the right. This needs to stay right, so I need like another statement. Now, if it starts back up, it's going to go to the left, which is here. Here. That's not what I wanted to do. I want to get the vowel. I don't even know how to think about this problem to solve it. My brain, it burns. Oh man. Oh man. That did not make it any better. Brain freeze. Brain freeze. Okay. Oh. Not any better at all. Don't do that. Okay. To you more intelligent software developers out there, there's no need to make fun of me as you watch me try to figure this out. Or not intelligent, but skilled. Like you understand what this is trying to tell me to do. Still need to go left, right? I think I'm gonna have to go look at other people's and just make notes and hope I can figure out the medium ones. So I don't. And if I pull up this, they have the node priori, right? I'm trying to learn the iterative, but I'm not trying to learn the recursive route, not right now. They only show the recursive. Let's see. Yeah, I'm only faster than 7% of people. Ha 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 ha. I'm not looking for speed, I'm looking for understanding. Oh, wrong solution. Yeah, whole problem with this is very different from what they got rid of the second while loop. So I guess I don't understand why I needed the while loop. So I can go back up and down the tree. And if I don't need to go to the tree and I just need to put it in the order that I'm seeing, I wouldn't need the while loop. That is the only reason why this would work. If I just need to get all of the values, That's like really the only reason that would work. So I guess I'm not traversing it if it's in pre-order, not really. Um, Iteration and recursion. I just want iteration right now. Not trying to learn incursion. That is not my goal. So they start their stack and they just pop the first one off. And if current node, pin the value, pin right or pin left. So I guess that is the point. If I'm not having to actually traverse, go up and down in an order, it'll just naturally do it without this statement. So I need the while to go through the whole length of it, but it doesn't seem that I need anything else. That was recursive. I want the so I just need the if statement. If root, just get the value. And I'm gonna have to make notes in my Cody book. Yes, I have a book dedicated to code notes. It is here where I write code and make notes. It is very unfortunate, but it works. So I'm gonna have to write code and make notes about all three of these before I understand it to do. Other ones. I'm gonna have to see how this walks through. If this had been easier, I would say I'd make a fair computer science, like software engineer. This isn't coming easy. And this is also why just because someone has a high lead score, it doesn't mean they understand anything. Because you can just get the solution off of someone else and their solution. Plenty of people making videos about each one of these. The question is, did you use to just copy and boost your lead score, or do you understand why that is the solution? So my goal is specifically to learn stack from an iterative standpoint at the moment. That's all I want to know is, can I use these easy ones, learn the thought process, and apply it to the medium ones? That is the goal. So this worked for 2 out of 3. And let's see what I did different. I went left first, and I lit left twice. So this should be right. I was trying to be different. It shouldn't matter, right? It does matter. So why does it matter? Let's look at the description. So I need to go right first because there's nothing to the left. Maybe. But it should work no matter what. I should be able to put any binary. Let's go back. If head, res a pin, root vowel, put her stack in. If root left, stack of pin, root of left, root right. Yeah, that was it. Misspelling here. So, how I choose to traverse depends on the ordering. Just going in order, I would only need one loop to loop through and just pick up all the values by telling it to go left if there's left, and if there's not left, to go right and to switch the cursor over. That's this one. So that brings us to the next one. But before, I got a wrong answer in the submission. This is good. It is great for learning. Oh no. So it did move the 2 in the wrong spot. So let's put right first. And then we're going to have to spend time figuring out why if I don't go right first. This is wrong. Is it LeetCode? Is it me? Okay. This is a fast solution. So, why must I go right first? We have answers. Oh, man. This is my last problem for the day. I don't care. For pre-order traversals, the one we did first, we need to go to the root node, then visit the left subtree, the right subtree. For in order, visit the left subtree, visit the right subtree, then visit the right subtree. Right subtree. So root left right is then left right root, left root right, and then man. I guess I need to memorize this because that's the next one I'm about to do. So to do it is left right root is post. Oh man, the burning pain. Okay, start. Pre-order traversals prioritize the root node, then processes the left tree, and finally the right tree. It's ideal for the scenario where you need to explore roots before inspecting leaves, such as when exporting a tree structure into a file that can be reconstructed. If the tree is empty, return an empty list. Initialize the stack with the root node. Continue until there are no nodes left to process. So remove the last element from the stack to process. If node, visit the node by adding its value to the output list. Push right child first so that the left child is processed first, maintaining pre-order. If right, append right node. If left node, return. This ensures the root node is processed before the subtrees, which is essential for operation where the roots needs to be visited. Tree climbing. Terminating the condition expected. The loop continues as long as the stack is not empty. This condition ensures that the traversal only stops when there are no more nodes left to visit. Initially, the stack contains the root node, and the nodes are added to or removed from the stack as the traversal process. Yes, it's very tiring, brain draining, and all the other stuff. Iterative logic. The stack facilitates backtracking to the parent node, ensuring nodes are visited in pre-order. Pushing the right child before the left ensures left nodes are processed first, adhering to the pre-order sequence. A stack is used to manually simulate the recursive call stack, helps backtrack into the parent node. Then it goes in order of operation, pushing the right child before the left ensures that the nodes are processed in correct order. Node, left, right, left. So that if I push the right child first, I process the left because I pop it off first. Because it was the last in, first out. Tree copying the expression trees, creating a prefix notation. Direction and structure. In order traversal, left, root, right. So in binary search trees, it wants the natural order, which is so pre-order, root, left, right, root, left, right. Yeah. And in order would be left, root, right. Which is what I submitted here. Append the current root, go to the left, pop the right, append that value, go to the right. No, hold on. Pop the left because left goes off first. So this is more for binary search, finding the smallest or the largest element and sort. So this is binary search. Okay. Post order, left, root, right, left, root, right. No. Left, right, root. Oh, man. The notes today are going to be something fierce. Child nodes before their corresponding parent nodes. And to do that, you do the same thing, but you're going to have to start with popping first and then appending the node. And then left, append left, right, append right. So pop, set the node to the first thing, pop, and append that to the stack, and then left and right. So I have to use two stacks. Stack 1, stack 2. So I need to append the node to stack 2 after I pop stack 1. First stack is used for the initial traversal, while the second stack serves to reverse the order. So if you needed to reverse something, I need two stacks, one for the original and one for the reversal. Yeah, I remember that from my stack lesson yesterday. Then I traverse the tree. The initial root node is pushed to stack 1. As we iterate, each node popped from stack is pushed to stack 2, ensuring we process in reverse order. Pushing the child to the current process node on stack 1. The left child is pushed before the right, ensures upon reversal. Continues until this first stack where you push the original one is empty, so that every child in there was processed. And then it makes it more efficient since you're not having to go from beginning to end. And this is more of tree deletion, dependency resolution, space evaluation. Okay. 1, we're bookmarking. I don't have an algorithm, so, but we just made one. Thank you, kind sir. And now we're going to go to the problem set list, go to the post-order traversal, and see if I can't remember what I just learned on the fly. I need stack 1. I need stack 2. Now, while not root, no, while root or stack 1, we're going to create the node, and this is going to be set to stack 1 dot append, no, pop, and then we're going to have stack 1 dot append root. Then we're going to have if node dot left stack 1 dot append root. If node dot right stack 1 dot append root. Okay. Don't think this is right, but I'm going to run it anyway. Oh, yeah, beat that. Yeah, I'm popping from an empty list. That makes no sense. You lied to me. Stack 1 pop. Oh, I assign root to stack 1 according to his root.pop. This actually for me would be root.root.pop. I don't think this part matters. Let's do this one. This should be stack 2. Yeah, I'm screwing up stuff. So, I'm trying to do it my own way. Root.left. Aha. So got that case, but didn't get this case, or didn't get that case. Okay. This guy uses continue. I guess maybe I can't actually do it this way. I really do need to save it. Okay. Does it? Let's see if it actually changes something if I change these to node. If not, I'm going to take some time to study this. But I have to get off. I have to do meetings. I've been meetings all day. It's Tuesday. Worst days ever to code. Meeting days. Okay, yeah, I'm gonna have to come back tomorrow. I need to go to a call. But it was good. And thanks for tuning in if you are tuning in. If not, I'll see you tomorrow.